Okay, you might be wondering why I'm hiding in a telescope. Well, it started when I was talking to some of my friends at the Further Math Support program about how much I love mathematics, and I think it's fun to do even if it's not necessarily useful. And they got a little offended. They said, no, A-level maths is definitely useful in the real world. And I said, no, it's not. And then they sent me to visit someone they claim uses maths in their job. However, their job is shooting lasers at spacecraft. So I'm here at a space laser facility somewhere in the south of England, and I'm going to meet someone who uses maths to do that. I'm here at a space geodesy facility where they do genuinely shoot lasers at spacecraft. Vicky here has very kindly offered to show me around and explain what they do. So, I mean that is my question. What do you actually do here?
We track Earth observation satellites via the laser.
Oh, so the laser's used to measure where the satellites are?
Yeah, precise range to the satellite.
Okay. And so I guess you shoot the laser at the satellite. Mm-hmm. It bounces back.
From a mirror assembly on board, yes.
Oh, so you've got a special reflector on the spacecraft?
Yep.
And you can time how long that takes?
Yeah, we've got very, very precise timers, so we time tag it as it goes out, essentially.
So you know roughly when it goes out?
Yep.
Or quite accurately when it goes out?
Quite accurately when it goes out.
Okay, and then you know when it comes back?
Yep.
You know the speed of light?
Yep.
Through the atmosphere?
Yep.
And then quite a simple calculation, I guess.
Very
knows
simple
you
calculation.
exactly how far away it is. I think that is doing a disservice to just how complicated the whole procedure is. But as a concept, it's not bad.
Yeah.
Okay. In a very simple way, it's sonar, but a laser off a satellite.
Oh, very simple way, yeah.
Okay. As simple as I can. Now, what are these satellites actually doing? Why do we care where they are?
Well, they're all measuring the Earth somehow, telling you some information about whether it's ice cap melting, deforestation, ocean levels, temperatures, velocities.
So whenever I see a report that says the ice caps have melted or this has changed, mm-hmm. that's because of satellites going over. And for that data to be meaningful, we need to know where the satellite was when it took it.
Yeah.
And so that's why you've got to work out exactly where they
yeah.
are. Okay, amazing. So can you show me the data you get to start with, which is showing you roughly where the satellite should be?
Well, all the predictions come in on this computer over here.
Okay, so these are the predictions.
So these are the
spacecraft should be?
Yeah, so this is a list of satellites we can track over so many hours.
Oh, so it's time this way.
Yep.
Satellite that way.
Yep.
And roughly where they're going to be in those numbers?
It doesn't give you that much information, this screen. It just allows you to choose which satellites we want to track at what time.
So there's an infographic of which satellites are available.
Yeah.
And what you just click to select?
You click one to select, yeah.
That's so good. And then when you're up at the telescope, you can then choose which of these it's going to point at. And then
that's right, yeah.
Oh, that's so good. So where does this go to get to the telescope?
So that information gets fed to the ranging computer, which
is
the other side of the room.
Okay, here we go.
We've got a list of satellites.
Right.
And each satellite tells us, next to each satellite, tells us where it's coming up in our horizon or around us, where it goes to the middle of the path and where it ends.
Okay. And how far up in the sky it gets?
Yeah, maximum elevation it gets to.
Okay, and is that enough to find it?
Yes, so all of that information is held in the computer's head. Well, we don't know all the forces acting upon the satellites, so they can be slightly different than we expect.
Right. But that's pretty much enough to be able to pick it out of the...
Yeah.
Okay.
Yeah. So you can do a little bit of honing in on the satellites when you're up next to the telescope actually tracking.
Yep. Okay, so with all these angles and timings and calculations, undoubtedly there's some pretty serious mathematics going on, which the people in charge of all this have to do. But for completeness, I want to definitely find it in one of my textbooks. And what's great is, when I got this collection of textbooks, I wanted to get a range of books across different eras and different parts of the curriculum, so it was quite a broad sample of A-level mathematics. But when you saw this one, you didn't respond favourably, I'm going to be honest.
It's a little bit familiar.
Have you met this book before?
I have met that book
before. Was this
before.
your textbook at school?
It was one of them.
One of them. Well, not this actual copy.
Yeah, I had that textbook. I've got that textbook.
So good. Was maths not your favourite subject?
I wasn't very good at it.
But I mean, here you are now, shooting lasers at things. That's pretty cool.
I have to use maths.
So I know okay, I'm going to pretend that doesn't please me immensely. I'm sorry to hear that. But given that you are subjected to some mathematics, I'm going to find it in the textbook that you thought you were never going to see again. So, I mean, I've got trigonomic functions here for you. So sine, cosine, all of these things, because everything you're doing here is looking at the trigonometry behind all of these angles. There are some other bits in here where you're looking at doing calculations of rate, so the actual distances away to the spacecraft. But my favorite bit right at the back, just for you, is 3D points and coordinates in space.
Hooray!
And so I know you're doing that just to humour me, but it's fine, I'll take it anyway. So here we go, actually doing calculations, looking at where things are up in the air by measuring how far up you have to turn to look at them. And by using the timing, you then get that exact distance away. And so you look like you're tolerating this. I'm having a great time. Anyway, given that I'm probably having more fun here than you are, let's move on, because now that I know you're definitely using maths,
Definitely using maths.
I want to have a look at the laser.
Okay.
Okay, so I guess that's the laser.
That's one of them.
And that's a lot of air conditioning. I can hear the fans going like mad. Is that because the laser heats up?
One reason.
Right.
But we've got to keep the electronics very stable.
Fair enough. What am I up against?
So excuse the documentation on top.
All right, so someone's been making notes.
Yep.
And that's it, it's in there.
It's in underneath this blue box, yep.
That's it, there's just a little bit there.
Yep.
Wow. Okay, and where does it go? Because it's pointing that way.
So it actually comes outside,
Yep.
comes up here and round, and then into the tunnel down there.
Okay, so we can get around the other side
So
and
if
see
we run
that.
around the
Okay,
other side.
okay, around the other side. So where's the beam go?
So in this tunnel,
All right.
the beam comes inside
In here.
and then gets bounced out that way.
So there's a mirror in there somewhere.
There's a mirror in there.
Okay, and it comes this way.
Yep. And hits the mirror.
Oh, I can see a mirror.
Yep.
Okay, so there's a mirror in there,
Yeah.
and then it goes straight up
Straight up.
through the roof.
Through the roof to the telescope.
Okay, so for that we got to loop around.
Yeah.
Okay, so this is the actual laser and telescope.
Yep.
That's fantastic.
So before you go any further,
Yeah.
you could go and hit that green button down there.
This one. Whoa! Oh my goodness. That was as loud as it is suddenly bright. So, of course, we're going to be able to point the laser up into the sky at the satellites. That's so cool. So where does the beam come out once it gets to here?
Right, so the beam comes up from downstairs,
Yep.
hits a mirror in the middle of the telescope,
Got
yoke,
it.
off to another one here,
Oh, okay, so there's the mirror
That's
there.
another mirror there.
Yep, and it comes up
Another
here,
mirror there.
another mirror there,
another mirror here,
another mirror there.
and out of the emitter telescope.
Oh, and this is out on the side here.
Out the side, yeah.
Oh, that's fantastic. So the actual laser comes blasting out of here and hits the satellite
Orbiting the planet, yep.
somewhere up there. And then this is the telescope, which is a glorified photon detector, right? It's just trying to
Yeah.
find... No disrespect to the telescope. Right, and so where do you actually detect the photons coming back?
That would be, so they come into the main telescope,
Yep.
get focused back onto a detector right at the back of the telescope.
Oh yeah, there it is. Look
Is
at
our
that. So
detector.
That's it. That's all that effort to get a photon into that.
Yes.
Oh, that's so good. And how many? Okay, so this detects a single photon.
One photon.
And is it deliberately one photon, or is that just all you're kind of getting?
No, we're deliberately controlling the return rate into that detector
Yeah.
using filters.
Oh, okay. So you don't want any extra photons.
We
You
don't
want a
want
single
extra
photon.
photons.
No problem. And how many photons do you send out? So when you fire the laser out of here, how many are going up for every one that comes back down?
So it's approximately, I can't remember the exact number, but it's 1.7 times 10 to the 17 photons in one
Okay, well,
pulse.
that's two significant figures.
Yeah.
That's fine. 10 to the 17.
10 to the 17.
What's that? It's like 100 million billion. Well, what's a billion? 10 to the 9. We can do this.
Do we use billion in the UK?
Oh, wrong billion. Ah, it's a lot.
Yes, it's a
It's
lot.
a lot. 1.7 times 10 to a lot. Of 10, okay, 10 to the 17 photons. That is a fraction of a fraction that you end up getting back.
Yeah.
That's absolutely incredible. So before you lined up some satellites. So
Yeah.
I guess, would you normally run it if it was this cloudy?
No. No,
Right,
we
is
wouldn't normally run it in
Is
when
it
it's
just because you
cloudy,
can't, the laser's not going to get to the
We
satellite?
we can run it, but we just can't fire the laser
Oh, okay.
at this point in time.
Okay, but okay.
So we can get it
So
going.
we can fire it up, but we can't shoot any lasers into the sky.
Yeah.
Oh, okay.
So
So how do you
going for
actually
something
turn it on?
arbitrary.
This is so good.
So we've got a list of satellites here
Right.
that we can track. These
Oh, yeah,
are
there they are from before, and is it their latitude and longitude?
these are where they're coming up in the sky.
Yep.
Where they're in the middle of the pass. And in
Oh.
the pass. This is height. So
Yep.
elevation.
So that's just where they're going to appear on
Yep.
the horizon,
Yep.
how high they're going to get, and where they're going to go down.
Yeah.
Oh, okay. And then the times they're going to do that.
Times we can start firing the laser, and times we have to stop. So at daytime, it's 30 degrees above the horizon. We can start firing.
And why is that? Just because the amount of atmosphere it's got to go through, or is that?
30 degrees.
Yeah.
It's basically the dome
Oh,
where
it's where the dome is.
it's where the
You
dome
don't-
is.
It's not good to laser your own dome.
No.
It's fine.
Plus, it's slight visibility for seeing things coming.
Oh, okay, right. Okay, that makes sense. That makes sense.
So each one of these satellites has a arbitrary pass number next to it.
Okay, yep.
So we'll pick one of those, 559, next one, first one on the list. If we type in the pass
the
number,
pass 559.
559, so hit return.
Oh, this is great. I do enjoy pressing buttons. And nothing has happened.
No,
Is it sending the information?
It's sending the
Okay, right.
information.
Oh, here we go. So how does it know where to look?
So we start off with a prediction telling us which satellite it is,
Yep.
the velocity that satellite's moving at, how high it is, where to start, where to stop. So we know whenever it is on the path, so we can go to it.
Right.
And catch
and
it up.
so it knows to hit that bit in the sky, it's
Yep.
got to twist a certain distance, lift a certain distance.
Yeah.
And so technically it's pointing right at it.
Technically, it's pointing it right at it, and that
Well, it is
buzzing
pointing
in the
right at
background-
it.
Yeah, yeah. The
What's
buzzing in the
that?
background, which
Yep.
I'll switch off, is the radar going off because we're looking at cloud.
Oh, so it's there going, you idiots, you're
Yeah,
looking at cloud.
yeah.
What are you doing? Okay, I'm glad you got a buzzer for that. Okay, so we can't actually send the laser off.
No, we can't. Sadly, sorry.
That's fine. Okay, that is really, really good. Now, one thing we haven't mentioned is how dangerous lasers can be, which is why you just gave me a pair of goggles. I suspect a little too late. But, okay, so I mean, people have a general idea that lasers are quite dangerous. Like, I assume the ones you use here can do some serious damage.
Yeah, they can do some serious damage.
Good. I'm glad we covered that. What about like laser pointers at home? They're a lot safer.
I personally hate laser pointers.
Really?
Absolutely detest them.
But you're a laser professional and you hate laser pointers.
Well, the reason being is because I work with lasers all the time. I know how dangerous they can be.
Right.
So, and I bought one off a well-known company on the internet.
On the internet?
On the internet. And it was supposed to be safe for using on whiteboards.
Oh, like your standard laser pointer job.
Yeah.
Okay, right.
And I went to use it, and you know, because I know about lasers, I knew that
You looked at it and you went, that looks brighter than a safe laser should
definitely
be.
brighter.
All right.
So I took it downstairs onto the test bed.
Because you're like, well, I've got a laser lab.
I've got a laser lab. I
So
can do
good.
it. So I tested it.
Yep.
And it's supposed to be 1 milliwatt.
Yep.
It peaked at 28
28, so it's 28 times more powerful
than it should have
than
been.
a claim. That is definitely, so if someone got that right in the eye, that could do some damage.
That would do damage.
That is terrible, right? So something like this, though, will keep you safe.
From particular wavelengths.
Oh,
Yeah.
so this blocks a certain wavelength.
Yeah,
so that's,
so-
I mean, I love the fact that it keeps you safe and it keeps you looking cool. Check that out.
Oh, yeah.
All right, so I've always wanted to start a steampunk band. So anyway, it's been a good day. Do you mind if I borrow these for a second?
If you must, yes.
Okay, I will. Anyway, Vic, it's been absolutely brilliant. Thank you so much for showing me around.
Been a pleasure.
Thanks very much.
Bye.
So it turns out shooting lasers into space does require a few calculations. But what caught me off guard is while I knew that of course trigonometry and 3D coordinates and latitude and longitude is all in A-level mathematics, I thought afterwards people would, you wouldn't have to do it yourself, your sat-nav would do it. But now I realise there are people like Vicky who have to actually do those calculations. And what really delights me is that Vicky doesn't like maths. She had to learn it and now she does it to make it possible to do all the other stuff that she does enjoy doing. And given that the details and the data coming out of these spacecraft are used by people studying tectonic plates or deforestation or ice caps melting, all these people in different industries have to do this maths in their job even though they may not like it. And I know it sounds a bit sadistic that I get a little thrill from that, but I think it's great that this maths is used in so many different industries. But for now, I'm just going to head off as quickly as I can before Vicky realizes I haven't given these goggles back.